Okay, it's my pleasure to introduce Alan McLeay from University of Luxembourg. He's going to tell us one of the latest developments in infinite type surfaces.
Yeah, thank you very much. I'm not sure these are the latest developments, but they're I think they're very interesting developments. And yeah, as Funda will know, I've chosen the colors of the Luxembourg flag to highlight my talk. So, okay, I'll just cover the title, first of all, Homeomorphic Subsurfaces. This is a kind of cool phenomenon that appears in infinite type surfaces, which we'll get onto in a second. And then omnipresent arcs is kind of our main definition. And when I say our, I mean Federica Fanoni and Tai Gaswala. Okay, so I've just learned that there's been no other talks on infinite type surfaces in this seminar. But that's fine. The definition is very short. A surface is finite type if the fundamental group is finitely generated, and otherwise it's infinite type. Okay, and infinite type surfaces all have these things called ends, and ends are what you think they are. They're kind of, if you embed your surface in R3, the ends of the points which reach infinity in some naive sense. So, I mean, some finite type surfaces have ends too. Every puncture is an end. So here's a punctured torus, and there's the end. Kind of, if you embedded that in R3, this be kind of flying off to infinity in some way. So punctured torus has an end. This is the Loch Ness Monster. This is everyone's first infinite type surface that we meet. It's just, you take a genus 1 surface and you glue another handle on it, and then you glue a third handle on it, glue a fourth handle on it, and you keep gluing forever and ever and ever in one direction. And that direction is exactly the end, off to the right hand side here. So the Loch Ness Monster has an end also. Yeah, this is the nice thing about infinite type surfaces, because the classification, there is a classification, but it's slightly harder to state than finite type classification, where it's just the genus and number of punctures. So what we do for infinite type surfaces is come up with, charming names that describe pictures of them. So here's the flute. I guess it's an infinite flute. And we have all these, it has infinitely many ends here and here, all these punctures, and they go off to infinity. And their accumulation point on the right-hand side here creates another end. So the flute has countably many ends. And it's actually kind of, in some naive sense, countably many ends plus one. Just as one extra end that's more special than the other ones, without defining special anyway. Okay, and then so that's some surfaces, and then here's the blooming Cantor tree surface. So this is a kind of snapshot of it. Obviously it's infinite, and the way you construct it is by gluing. You take a genus 1 surface with 3 boundary components, and you just keep gluing them together in every direction. So it's almost like you could imagine an infinite trivalent tree where every vertex has genus or something kind of strange like this. So that's the blooming Cantor tree, and that has infinitely many ends also, just like the flute, but actually its ends form a Cantor set. So there's this notion of the end space for each surface, which you can kind of apply topology to, and that topology comes from the surface. But that's kind of, and so that's really important for proving things about in particular, proving two surfaces are homeomorphic. You need to really think about these end spaces, but I'm going to avoid doing that for this talk, and instead just draw some nice pictures, and hopefully that will get my point across. Okay, so that's kind of crash course on infinite type surfaces. Here's a crash course on arcs. Now, an arc for us, well, first of all the surfaces we consider will have no boundary at all. So when I say arc, I don't mean the endpoints are on the boundary. I mean some proper embedding. So these arcs don't self-intersect. And all their accumulation points are where they should be on the arc. This embedding of the interval 0 to 1 that somehow extends so that 0 gets associated to an end point of the surface, and so does 1. I hope that makes sense. So you can't have arcs that kind of live off in the middle of nowhere like this. They kind of have to be anchored to ends of your surface, ends of any type. So there's lots of types of arcs. They exist on finite type surfaces also, and infinite type surfaces. So this is a non-separating loop. Here, that's the red one. I call it a loop because endpoints are the same as a unique endpoint. It loops back to itself. The blue guy is I call this a two-ended arc because it has two distinct ends. And as I said, these exist on infinite type surfaces too. So you see this infinite type surface kind of, it's like the Loch Ness Monster we saw before, but it has your glowing genus in two directions forever. This is called the ladder surface. Okay, so that has a two-ended arc too. The red one, two-ended arc. And it has a 1A, it has this loop again, but this turns out to be a separating loop. So what I mean by that is if you cut along that blue arc, you get two distinct components in the complement. Whereas the non-separating loop we saw in this genus 1 surface, if you cut along that, you have one connected component. So what we're interested in, at least for the first half of this talk, are the kind of homeomorphic types of arcs. So if you can apply some homeomorphism to the surface, it takes arc A to arc B, then we say those two arcs are of the same type. So what this is really a question now is you kind of take the complement of the arc and you look to see if the surface you get is homeomorphic to the one you to some other one. Okay, sorry, I'll say that again. So you have two arcs, A and B. You take the complement of A, you take the complement of B, and you look at these complements, and if they're the same, then there's a homeomorphism between these two subsurfaces, and this extends the homeomorphism of the full surface. So you can say that these two arcs are of the same type. Okay, and when I say take the complement, I really mean the complement. Sometimes when you cut along curves or cut along arcs, you know, maybe some of you do this in your spare time, what you'll often do is if you cut along a surface, you usually consider that as a boundary component. Something isotopic to that curve will end up as a boundary component. That isn't what we're doing here. So the surface we start with has no boundary. Then the surface of the complement of some arc, sorry, the boundary of the complement of some arc also has no boundary. So we're removing the arc completely, and then yeah, we kind of aren't filling in the gaps we've made or anything.
Just a quick question. What happens to so the arc is anchored in, you know, between 2 points, ends. So when you're removing the arc, what happens to the ends?
That's exactly what I'm going to talk about now. Exactly this. I mean, this is really the question. Yeah, what does happen to the ends? It's not clear until you do some work. So here's just, we'll just go over that same question for finite type surfaces to remind ourselves what happens. If you remove this non-separating loop I've drawn in this surface, your subsurface is as follows. So you start with a surface of genus 2 and 3 boundary, 3 punctures, 3 x's, I've drawn them as here. And then when you cut along this red arc, what happens is you lose genus, first of all, and it's almost like your end gets split in half. So the general rule here is that a genus G surface with n ends, n punctures. This goes to a genus G minus 1 surface with n plus 1 punctures. So that's the rule. And the story to remember this is how we're going to remember this going forward, is as follows. If you cut along a non-separating loop, you lose genus and the end splits. Okay, that's what happens. So that's non-separating loops. And what this tells you actually, if you
do you put metric on this surface use? Is the limit harmonic structure?
For now, no. I'm just thinking about these as topological surfaces. Yeah. So right, what this tells you though is that every non-separating loop is in the same it's in the same orbit, you know, the same mapping class group orbit or homeomorphism group orbit or something. This is the only picture that can happen if you have a non-separating loop up to, you know, topology. Okay, so that's non-separating loops. Separating loops. Here's the same surface. Now we cut along this separating loop, and now because it's separating, we have 2 components in the complement. The first one in this case has 1 puncture, 1 genus, and the other one has genus 1 and 3 punctures. So the general rule here is maybe harder to write down, but you take a genus G with n punctures and you send it to a genus G plus 1, genus G1, N1, genus G2, N2, where G1 plus G2 is equal to G. And let's make sure I get this right. N is equal to N1 plus N2 plus 1. So this is the general rule. So now you can see there's a lot more types of separating loops on finite type surfaces. Still, I mean, finitely many per surface. Okay, but the story to this, what's the story? The story is the surface splits. You can't avoid that, it's a separating loop. So the surface splits and the end splits. Okay, so finally we have 2-ended arcs, and here the story is very different. When you cut along this or you remove this arc from your surface, yeah, what happens is, you know, any disk, let's say, that surrounds both punctures in the complement just surrounds one. Yeah. Okay, so the general rule here, you have a GN surface. And what does it go to? The genus stays the same, and the number of punctures gets reduced by 1. So our story that we're going to tell ourselves here is that the 2 ends, because this is a 2-ended arc, remember, so there's always 2 ends. are fused. Okay, so all these rules kind of fail instantly when you think about infinite type surfaces. I mean, because these classifications don't exist anymore. You don't have a finite number of genus necessarily. You don't have a finite number of punctures necessarily. So this doesn't work. The good news is that all these stories we've been telling ourselves all the way through, these are all still true. But now this kind of implies much more interesting topological phenomena that happen. So again, I'll just look at some examples. Here's infinite type surfaces now. Here is a first example is non-separating loops. And I've drawn two different red curves here, two different non-separating loops. The first one, so this one here, the top left, you look at this arc. It has kind of two sides to it, the side at the top, side at the bottom. And the side at the top has, as you travel to the right of the surface, there isn't any genus anywhere, or finitely many genus. And if you travel along the bottom, so maybe this half of the surface, you'll see that there's infinitely many genus. Infinite genus. So the story, as I said before, is for non-separating loops, the end splits and you lose genus. That still happens, but losing genus suddenly doesn't seem that important for infinite type surfaces when you have infinite genus. So all that really happens is that the end splits, at least for this surface. And so the only interesting question now is, well, what happened, what are the ends? What does the end split into? And for this arc I've drawn at the top, the end splits into one type of end which has all this genus accumulating near it, and then just this planar end here, this puncture. However, if I drew my arc slightly differently, as I've drawn it in the second picture down here, you can see that this arc now, weaves in and out of these, genus 1 subsurfaces, kind of weaves in and out all the way from infinity back into the surface and back out again.
Yes.
Okay. Was that a question? Sorry. No. Right. So what happens here is the end still splits, but now the topology is different of both these ends. So, well, one of the ends. One end stays as this end accumulated by genus, and the other end is, this kind of, so you have kind of two copies of this Loch Ness monster that appear now. So that corresponds to this subsurface and this subsurface. Okay, so these things are kind of tricky to keep track of. But the point is, the surface, the complement of this surface, so sigma minus alpha, varies depending on alpha. And that just wasn't true for non-separating loops for finite type surfaces. Okay, and then there's kind of similar stories for separating loops and two-ended arcs as well. So the story is the same, it's that the surface splits and the end splits, but how it splits depends on your choice of arc. It will always separate the surface because it's separating. You have to really be careful and keep track of the topology of the ends when you're removing this arc. So here's two-ended arcs, different surface this time. The story here was that the ends are fused. So if I'm fusing the two ends here, the two endpoints of this red arc, one of these ends is a limit point of all these punctures. Another one is some accumulation point of all this genus. And so the fused end has both these characteristics. It's accumulated by both punctures and genus. A different two-ended arc, for example, a two-ended arc where one of the ends is just a puncture. Again, you do the same thing. You think about fusing the topology of these two ends, a puncture and this kind of Loch Ness monster shape. But the topology of that is just a Loch Ness monster. The puncture doesn't add any topology because it's the only boring end, effectively. So the upshot of this, at least the second example, is that these two surfaces are homeomorphic, even though one is a proper, well, not proper subsurface, but it's a subsurface of the other one. And yet it's homeomorphic to the one we started with. Which is interesting. It doesn't happen often in finite type surfaces. And it kind of begs the question now, what is an essential arc? So I'd like to answer that now. An essential arc for finite type surfaces anyway, in fact for all surfaces, let's just say, an arc is essential if no component of its complement is homeomorphic to R2. That's a reasonable definition of essential. And these kinds of essential arcs are very useful for areas of studying surfaces, from studying mapping class groups, from a geometric group theory point of view anyway. Essential arcs are the things you look at. And this is equivalent in finite type to the following definition, which is that an arc is essential if no component of the complement is homeomorphic to the surface you just started with. These two things are equivalent in finite type. But we've just seen an example where this isn't the case in infinite type. You can take a non-essential arc, which gives you a homeomorphic subsurface. Okay, so the second condition is significantly stronger than the first one. Okay, so like I said, I mean, people study essential arcs. The example I'll talk about for the rest of this talk really is the arc graph, which people might have seen. Yeah, okay. But at least for the purposes of this talk, I will give this second definition a new name, which is truly essential. Okay, so an arc is truly essential if its complement, if none of its complements are homeomorphic to the thing you started with, the ambient surface. So let's take a look. This is a nice example. This is topologically, these two definitions I've given are the same. So either R2 minus a Cantor set worth of points. It's certainly an infinite type surface. Or this punctured Cantor tree, which is similar to this kind of Cantor tree surface we saw before, but now the genus is 0. So you're just gluing pairs of pants forever in every direction onto this surface. And then I just add a puncture in the middle, this extra puncture. So now we will just investigate all the types of arcs you can find on this thing. So the first one here, it's you can see there that shaded region is homeomorphic to R2. So this is a non-essential. Which implies that it's not truly essential. That's how the implication goes. The second example here, it's just a loop based at the puncture, but this time it's an essential loop based at that puncture. So it's going to have two distinct components in its complement, but each of them is going to be homeomorphic to the thing we started with. Yeah, this puncture kind of splits in half. So in the complement, you get two copies of this puncture, one in each component. So this is homeomorphic to the thing you started with, which means this is not truly essential. Third picture, here's an arc which has endpoints out at the Cantor set somewhere. The way I've drawn it looks like these ends are distinct, but they could also be the same end. Right, but the point is you're kind of fusing two points in the Cantor set together, which gives you a Cantor set as a result. That's the kind of homogeneous nature of Cantor sets. So this is also not truly essential. It isn't. The way to think about this is kind of, does the surface even notice when you remove this arc? And it doesn't, because it remains homeomorphic. So the final example is an arc based once at the puncture and then once out at infinity. And now here, the complement of this thing is homeomorphic to, well, it's just not homeomorphic to sigma. Let's just say that. Because really what happens is you're losing the puncture. The puncture and this Cantor set ends are getting fused, and because the puncture has no topology, this just essentially means the puncture is disappearing. So this is truly essential. Okay. So what I'm going to do now is give you an application for these truly essential arcs. So it's an application that works for truly essential arcs, which does not work for essential arcs in the infinite type setting. And that application is the arc graph. So this is seen quite a lot in the study of magma class groups, finite type surfaces. There's kind of lots of graphs that are built this way, where the vertices are the isotopy classes of arcs, similar to the curve graph. The isotopy classes of arcs, and the edges are between two arcs that have disjoint representatives. So this is a really useful tool. Some of its properties for finite type is that there's a natural action of the mapping class group. That action is very nice, and also it kind of describes all the automorphisms really of the arc graph. This is also a delta hyperbolic space. That's a nice property, and it is infinite diameter with unbounded orbits. Mapping class group action. Its orbits are unbounded. So what are the properties? So does this carry over to infinite type surfaces? Well, yes, there is. You do get property 1, there's a natural action. Property 2, for this particular graph, isn't known. Kind of more light is being shone on this, and it's looking like this might be true. But we don't know for sure yet what the automorphism group of this graph is. Let's ignore 3 for now. 4, this is not true. This graph is no longer infinite diameter.
Sorry, Alan, do you take the vertices to be truly essential arcs for this graph?
Well, for finite type surfaces, it's the same thing.
Okay, you just take all of them for the infinite type.
I'm just taking every essential arc for now.
Okay.
Yeah. But the problem is, if I do that for infinite type surfaces, then in general, this the diameter is no longer infinite. And you can see that I've taken 2 arcs that intersect a lot here. I'm not even sure what I've drawn, to be honest. It's just a bit of a mess. They intersect a lot, but no matter how much they intersect, I can just always, find an arc like this or something that's disjoint from both. Essentially what's happening here is because all the intersection of these arcs kind of has to happen locally to the 2 arcs. If you pick a, if your surface is big enough, if it's infinite type, it usually is big enough, then you can show that these things are not diameter or not infinite diameter. Sometimes they are, but in general they're not. It's diameter 2. For curved graphs, it's always 2. Okay, so that's a bit of a shame because this infinite diameter quality has been used by some people to prove some things. So, so that isn't going to work for infinite type surfaces. This arc graph, which I've called the essential arc graph, but it's just the arc graph. So now let's graduate to the truly essential arc graph for infinite type surfaces and see if that is any better. And it turns out it is, at least for this surface we just looked at, this R2 minus a Cantor set or punctured Cantor tree. So this was actually called the ray graph, and it was studied by Juliette Bavard. In what she showed for this surface, this truly essential arc graph is infinite diameter and also delta hyperbolic. If I have time to go over the proof of the main result of this talk, anyway, that also carries on to prove this. So that's pretty cool, and it suggests that maybe, you know, every time we should think of essential, every time we want to think of essential for infinite type surfaces, maybe just replace it with truly essential, the stronger condition, and we'll be able to build graphs that kind of do what we want, and you know, because somehow these arcs see more of the surface. This turns out not to work, which is a great shame. So here's why. Here's just a crazy infinite type surface that I've cooked up. It has so it has these things here that look like Loch Ness monsters, and then it has these things here that look like flutes, and they alternate in 4 different directions at once to give you an extra 4 ends on your surface. This is just a big surface. Right. And why is the essential arc graph on this surface not infinite diameter? The problem comes that when you consider arcs that look like this, so they join one of these flutes to one of these monsters, you know, one of these 2 towers together. And remember, if we go back to our rules of what happens here, when you take the complement of this, these 2 topologies are kind of forced together, and you get some weird looking end like this. And now this surface, so the complement of that red arc that I just drew, is no longer homeomorphic to the thing I started with, because I have this weird kind of half flute, half monster end in my surface, which didn't exist before. Okay, so that kind of arc, is this kind of arc is truly essential. Okay, but the point here is that the mapping class group orbit of this arc is just so huge, and you can kind of find a copy of this arc or something that looks like this arc with almost anywhere in the surface. So you take 2 arcs, you know, a red one like this, I don't know, does something crazy, and then a blue one that does something equally crazy. I think I've intersected myself there, but let's just pretend I haven't. So these things intersect, and they kind of, I don't know, take up all this space. The point is, my surface is so big that I can just find some truly essential arc way out here on the side somewhere. And this kind of proves that my arc graph is diameter 2. So no matter how crazy, I can just take 2 arcs that are completely crazy and intersect a million times. or infinitely many times even. But I can always find some truly essential arc which is disjoint from both. So this thing here is diameter 2. So that's a shame. However, so the way to think about this is when you take the complement of this purple arc, as I've drawn it, it kind of does damage to the surface, and the surface sees what you've done. But it's really easy to undo that damage. You can take an arc like this, some separating arc, and just remove all this from the surface. And now any damage I've done is being completely undone by this operation. So although the complement of the red arc, of the purple arc, sorry, is not homomorphic to the thing I started with, it's contained in some complement of a homomorphic subsurface. So that is, so okay, truly essential doesn't quite work, but omnipresent arcs, which is the kind of next step up in levels of essentialness. These are the things we're going to look at. So let's just define it carefully. Okay, just looking at the time there. A one-cut subsurface is just some component of sigma minus alpha, where alpha is an essential separating loop. So the kind of one very interesting result is that a surface is of infinite type if and only if it contains a one-cut subsurface, which is homeomorphic to the thing we started with. So not only do these homeomorphic subsurfaces always exist, we can always pick them so that the arc is an essential separating loop. Yes, okay. And a two-ended arc, we'll call it a two-ended arc omnipresent if it intersects every one of these one-cut subsurfaces. So let's first of all show you some things which are not omnipresent. Well, this example I drew here is not omnipresent because, like I showed before, I can cut it away with this blue arc. And then after cutting it away, the thing I have is homeomorphic to the thing I started with. So that is not omnipresent. You could come out from here and go up like that. And again, I can just draw an arc here that follows the red one and then cuts off this monster and follows the red one back. And I remove this. So kind of the complement of this blue subsurface is homomorphic to the thing I started with. Yeah, so you keep on just trying to see which arcs are omnipresent. And the answer is the omnipresent ones are the ones that run between these kind of two, or they run between at least, sorry, they run between two of the four giant ends. The kind of huge ones that exist on the extreme left and extreme right of my picture. Okay, so that's kind of in general what the omnipresent arcs are. And so here is the result, or kind of our application for these omnipresent arcs, is that we take the graph of these omnipresent arcs, the same as the arc graph and the truly essential arc graphs that I introduced, and we can prove this is connected, it's infinite diameter, it's delta hyperbolic, provided the surface is stable, which I haven't told you what that means yet, and there are at least 3 finite orbit ends. I haven't told you what that means either. So yeah, okay, to define a stable surface, I have to define a stable end, and to define a stable end, I have to actually give you a proper definition of what an end is, instead of just drawing pictures. So here is an end. So it's an equivalence class of a nested subsequence. Sorry, a nested, what do you call this? Nested chain of subsurfaces. Okay, so it's these subsurfaces U1, which contains U2, which contains U3. That goes on forever. And we'll say that the boundary of each UI, these things, yeah, these subsurfaces do have boundaries. Let's just say that's connected. Okay, and two of these chains are equivalent. So U1 is equivalent to this chain of V's. If eventually these chains kind of start containing each other, that's the point here. So if for all n there exist capital N where un is contained in Vn, and vice versa, by which I mean there exists some small m such that there is some big M where eventually the VM is contained inside the UM. So these kind of two things, these are chains that go off forever in some direction. And this equivalence is just saying that they're defining the same thing as they go off forever. So we can think about mapping class group orbits of these things. And so if the mapping class group orbit is finite, which in the previous picture we saw was here, that's exactly what was happening. There's the four big ends on the kind of extreme sides. So the mapping class group orbit of that is 4, but for all the other ends, the mapping class group orbit is infinite. Okay. So that's a finite orbit end. A stable end is one, and actually every end I've drawn, every surface you've seen has had only stable ends today. And I've only drawn 2 surfaces in my life which weren't stable. So a stable end is it's just where, as you kind of go out to infinity, you just get the same picture over and over again. So all of these UIs are homeomorphic. So again, if we go back to this example, maybe that's U1, and then this is U2, and then this is U3, and so all these shaded things I've drawn are homeomorphic. And the same if you define any of these ends. So this would be U1, and then this would be U2. So they're all kind of repeating and homeomorphic forever. So that's a stable end, and a stable surface only has stable ends. So I guess, okay, 5 to 15 minutes is what I read is my remaining time. Okay. Okay, so maybe I'll quickly give you a definition of a non-stable surface. As I've said, I've only drawn 2 in my life. I mean, once you know the definition, it's maybe easier to start thinking of them. But yeah, it's not obvious. So I'm going to construct it piece by piece. So I will call an end of type 1 to be this kind of monster. And then type 2 is this monster which also has punctures flying off to infinity. And then an end is type 3 if is a monster fused together with floats going off to infinity. So what I'm doing is I look at this end that I've called number 2, and every time I see a puncture, I replace that with a flute. And then, so you could imagine what n number 4 is going to look like. It's going to have infinite genus. And then every time I see a puncture in the previous picture, I glue on a flute. Okay. This is painful to draw. Right. So each of these ends, type 1, 2, 3, 4, these are all stable. You get this repeating picture as you fly off. These are all stable, but I'm going to kind of glue them together in a way that creates some non-stable ends. So the way to do that is, well, one way to do that anyway, is to think of an infinite trivalent tree, and you pick your favorite edge of that infinite trivalent tree, and you label the two vertices of that tree 1, and then every other node, every other vertex is labeled based on its distance away from a vertex of 1. So there are 2 vertices labeled 1, there are 4 vertices labeled 2, there are 2 to the n vertices that are labeled n. And then you use this as the skeleton of your surface. So you glue to vertex 1 an end of type 1, and you glue to vertex 2 an end of type 2. And you just go on forever like this. And what you end up with is this kind of weird picture here. And the key point here is that each of these vertices of type n, there are only finitely many of them. There are 2 to the n. But these Cantor set ends are accumulated by finite type, by finite orbit ends. Yeah, and this is what gives you a non-stable end, because here, as you progress out toward the Cantor set, you're not getting a repeated picture anymore. You're getting, an end of type 1, end of type 2, end of type 3, flying out to infinity. Okay. So that is a non-stable surface. They're very hard to picture and very hard to talk about, really. This isn't just in our work that they're hard to talk about. It's a really nice paper by Kazra Rafi and Katie Mann, where they also kind of have to not talk about these non-stable surfaces. And what they prove is that the mapping class group of these surfaces, they're generated by not quite compact sets, but by what's the word they use? Coarsely bounded, that's the word. Generated by coarsely bounded sets, which is some notion bigger than compact. But it allows you to say that the mapping class group has a you can talk about the big mapping class group up to quasi-isometry. There's a defined quasi-isometry type for these coarsely bounded generated groups. Okay, that's a bit off topic, but just to say that this phenomenon of stable ends and things is appearing all over the place. So that's the theorem. I'll very quickly, and then I'll try and take, well, I'll give you the headlines of how to prove it. The first is this, which an arc is on a stable surface is omnipresent if and only if its endpoints are finite orbit ends. That follows our kind of intuition from the picture we drew, but it turns out to be true in general. And the key fact is that there are only finitely many of these finite orbit ends on a stable surface. Because if you have more finite orbit ends, they have to accumulate somewhere, and that creates instability. Okay, so using those two facts, we can try and prove how this works. And if you're familiar with arc graphs, you might know these unicorn paths. which is how we prove it. So this is kind of all work, which I believe is due to Hensel, Przititsky, and Webb. We kind of got it via Durham, Finoni, and Glamis. So it's a really nice way of constructing a path in the arc graph between two arcs, two vertices. So you can assume they intersect, because if they don't intersect, then the path is clear. It's just one edge. And then the trick here is to then you start with an arc that looks a lot like the blue arc, and you slowly turn it into an arc that looks more and more like the red arc until you arrive at the red arc, exactly. So what do I mean by an arc that looks a lot like the blue arc? Well, you start, let's say here, you start at red. And then as soon as you intersect blue, you just start following blue instead of red. And you go like this on forever. And this gives you some red arc, some green arc here, which is connected to blue. It doesn't intersect it. But it certainly does intersect red. Okay, and then you just do the same again, but it kind of the next. So this first intersection point I picked was here. Then you follow along the blue arc to get to the next intersection point, which is here, and you just do the same again. So I follow red until I get to that intersection point, and then I start following blue. And now that's an arc that is disjoint from green. And I'm almost done, I think. Let's just delete this green one. And next intersection point's here. So I just do it again. And I guess there's going to be one more. I won't draw it. So that's sorry. So that's your unicorn path. And this is how you show this thing is connected by building these kind of things. The trouble for us is that our arcs can intersect infinitely many times. So you can do this same game. And so maybe this is your first intersection point, and this is your second intersection point, and then your third, etc., etc. And so what you're going to get by just following this exact same unicorn construction. Unicorn, I think, is one of the best names, because you know, it's a unique corner. So each unicorn is defined by a unique corner, and also unicorns are magic, and yeah, this construction is just magic. So right, yeah. So you can create this path, and it goes off forever, but it's never going to reach. You know, I'm saying these arcs intersect infinitely many times, so we're never going to reach an arc that looks like the blue one. Right. Okay, but what we are going to do is we're going to reach an arc. So what does it look like here? It looks like, wait, this done this right way around. I think I've done this right way around. So it looks like blue all the way up to here, and then it looks like red. But the point is, it's like, because I've said my surface has at least 3 of these big ends, there's all this space to work with now. I can just draw an arc like this. And so this isn't a true unicorn path, but this thing is contained in the one neighborhood of a unicorn path. So that shows you that for any 2 arcs, you can find a connected path between them. So the graph is connected. So that's how that works. And I guess I don't have time to talk about the proof of delta hyperbolicity. But if you look at any of these unicorn type arguments, showing that it's connected is the hard bit. Once you have that, you can use this extra kind of alternative definition. This is like the thin triangles definition. except instead of looking at geodesics, you just look at connected paths. But other than that, it's almost the same definition. Yeah, and the thing that you use, the thing that gives you this connected path is exactly these one neighborhoods of unicorn paths that we looked at before. So this satisfies this thin triangle thing, you get a delta hyperbolic. And then to prove its infinite diameter, the key point I said before is that there are finitely many finite orbit ends. So you can always find some subsurface, some finite type subsurface. This is called a non-displaceable subsurface. And you know that every arc, every omnipresent arc has to pass through this thing. And so you can just take one and then keep hitting it with some pseudo-Anosov, because you're in a finite type mapping class group now. So you can start talking about pseudo-Anosov elements. And this will give you an arc that's arbitrarily far away from the one you started with. Okay, so I'll just end by saying that our theorem requires 3 finite orbit ends. If there's 2 finite orbit ends, we don't know what happens. My suspicion is that this thing is not connected. Yeah. Maybe someone's proved this actually now I think about it, but I'm not sure. But the thing is, we really do need these 3 finite orbit ends, and 2, as you can see from this picture, this is kind of 2 elements of the 2 vertices of the omnipresent arc graph, which intersect a lot, and there's just no coherent way to build a path between them. Okay, so I will finish there. If you have any questions, please. Thanks very much.